Now, I won't go into detail on how E equals mc squared got figured out by Einstein, but it is all to do with his theory on relativity. But what it's saying is energy is equal to mass times speed of light squared. Amazing. So there's huge energy, because remember, this is 3 times 10 to the 8 squared was 9 times 10 to the 16 times the mass. There's a huge amount of joules in small amounts of matter. I think I've worked out in the past that I think a ton of coal could keep the average household going for 2,000 years if you could get the energy out of it. All right, so this is awesome. Now, how does it come into level 2, atomic and nuclear? Is what we actually do is when we see some of these reactions we've looked at, like U235 92 plus 1 neutron goes to barium plus krypton plus 3 neutrons, and I'll put the numbers on just so that we've got them again. The point is, if I said when I did this reaction that we had huge energy. So we don't see the energy here, do we? But there's a really important rule in physics called conservation of energy. So if there's energy over here being released that wasn't over here, where did it come from? And where it came from was what's called a mass deficit. A mass deficit equals the energy. So how do we figure that out? Well, we will do problems like this where we get the mass of this and this. So we add the mass on that side. Then we take this side and we add the mass. And we'll find that if energy is released on this side, then the mass on this side must be less than the mass on this side. So if we subtract the mass on the right side from the mass on the left, then we will have a little bit of mass left over called the mass deficit. If we use that mass in the equation, E equals mass times speed of light squared, then that'll tell us how much energy that reaction produced. You have conservation of not just these mass and atomic numbers, but you have conservation of energy here and here. All right, so that's how you figure out the energy. You can get reactions where the mass deficit's on the other side, where you actually, in this case, we had more mass on the left than the right, but you could have more mass on the right than the left, in which case you had to have some energy come into the left-hand side, and it gets converted into mass. It's amazing. So mass is not as constant thing as you thought, because if you're probably already going, well, where'd that mass come from? Because these numbers still add up, and they do add up. But the actual mass per nucleon in different nuclei is different. And we'll get into that more in year 13. But basically what happens is when atoms rearrange, so although we actually haven't lost any neutrons or proteins overall in the equation, their actual mass has changed a little bit when they got packed tighter into these atoms. So when you can pack your neutrons and protons tighter, you can release energy, and their mass has actually decreased than when they were in a different nuclei. And that's where it comes from. So that's how we use mass deficit to calculate our energy being released. Now there is another conservation law which I think you all know about, called conservation of momentum. So when these little guys, this reaction here, when this reaction happened and there was this huge amount of energy, where does it go? These guys get kinetic energy, but this one can't just shoot off really fast and have conservation of momentum. This one would have to shoot off in the opposite direction for the whole momentum thing to cancel out to be zero, because we're saying that these guys, if we say that these guys momentum at the start was 0, then this one must be 0. So there's conservation of energy and conservation of momentum.